In this video, we are going to look at 3 different exponent laws. The first law we will look at is what happens when you multiply powers with the same base. So to begin with, we have 7 squared times 7 cubed. Both the bases are 7. They have different exponents, but we are going to look at how we can write this as a single power, meaning just one base to an exponent. So here, this is already done for us where we have expanded form. So we have 7 squared, 7 times 7, which is here, 7 times 7. And then we have that multiplied by 7 cubed, which is 7 times 7 times 7. So now we can see that we have the base 7 multiplied by itself 5 times. So as a single power, that is just 7 to the exponent 5. In the next example, we have negative 2, which is our base, cubed times negative 2 squared. So I'm going to write out negative 2 times negative 2 times negative 2, which is negative 2 cubed, and then I'm going to multiply that by negative 2 times negative 2, which is negative 2 squared. So here, as a single power, I can see that I have negative 2 as the base, and it's being multiplied by itself 5 times. In the next example, we have 3 squared times 3 to the 4. So 3 squared is 3 times 3, and 3 to the 4 is 3 times 3 times 3 times 3. So as a single power, the base is 3, and the exponent is how many times I'm multiplying it by. So 1, 2, 3, 4, 5, 6. So it's 3 to the 6. Just a note, I wrote this example differently than I wrote expanded forms for the first example. The first example I used brackets, and the second example I used just multiplication signs. In the next example, we have y squared times y to the 5. So this example, we don't have a number as a base, but we have a variable y, which represents an unknown number. So we will just follow the rules that we already know. Y squared is just y times y, and y to the 5 is y times y times y times y times y. So now here, again, our base is still y, and we are multiplying it by itself 7 times. So it's y to the 7. We would not be asked to evaluate this because it's not possible because we don't know what the base is. We could be asked to evaluate the 3 examples above because we know what the base and the exponent is. As the exponents are quite large, we would probably need our calculators to evaluate those. In the final example here, we have negative 9 times negative 9 cubed. So negative 9 times negative 9 times negative 9 times negative 9. So our base is negative 9, and we are multiplying negative 9 4 times. So just notice that this negative 9 here has an exponent of 1. When we don't see an exponent, there really is an exponent of 1 there. We just don't write it when it's 1. So you should have noticed something as we were writing these examples as a single power. Each time when we are multiplying with the same base, we added the exponents. So 2 and 3, we got 5. 3 and 2, base exponent of 5. 2 and 4, exponent of 6. 2 and 5, exponent of 7. And 1 and 3, an exponent of 4. So now let's use what we found there to simplify each of the following examples. So we are just going to simplify here and not evaluate. So that means we just want to write this as a single power, but not find an actual answer. So in the first example here, we have 3 squared times 3 to the 4. So we know the base is 3, and then we simply add the exponents. So it's base 3 to the exponent 6. So this is now simplified to one exponent. Evaluate would then be use your calculator to find what 3 to the power of 6 is. The next example, -2 is the base, and I'm going to add those exponents. 4 plus 5, so like -2 to the exponent 9. Just a note, here the brackets are necessary because the base is negative. You absolutely need those brackets. In example A, you do not need those brackets. You could just write that as 3 to the exponent 6 because the base is positive. We don't need brackets. Example C, the base is 4, and we are now going to add 3 plus -5. So this is our first look at a negative exponent. So when you're adding a negative, that becomes subtraction. So base 4, 3 take away 5. So that's base 4 to the -2. And again, the base is positive, so you don't need those brackets. So it's just base 4 to the -2. And in the last example, we have base of 1/2, -4 plus 8. -4 plus 8 is +4. Here, the brackets are necessary because that exponent applies to the numerator and the denominator. So when describing the rule, we say that when you are multiplying powers with the same base, you keep the base and add the exponents. So that is the first rule of exponents that we are going to look at. Now, before we look at the second rule of exponents, let's just remember that 6 divided by 6 is 1, and what we can think of as crossing off. 6, cross off 6, we get 1. So here, if we have something a little bit more complicated, as 3 times 3 times 3 divided by 3, we can cross off a 3 from the top and 1 3 from the bottom, because that's all we have in the bottom. So we are left with just 3 times 3, which is 3 squared. Because multiplying by 3 and dividing by 3 are opposite operations, so they cancel each other out. So now let's look at the second rule of exponents that we're going to look at. Here we have base 7 with exponents, but now we're dividing instead of multiplying. So here in expanded form, we have 7 to the exponent 5, so 7 times 7 times 7 times 7 times 7, and we are dividing by 7 cubed, 7 times 7 times 7. So now let's cross off where we can, a 7 from the top and the bottom, another 7 from the top and the bottom, and another 7 from the top and the bottom. So we are left with 7 times 7. So as a single power, that is 7 squared. And the next example, we have -2 times -2 times -2 in the numerator. And in the denominator, we have -2 times -2. So here we can cross off -2 in the top and the bottom, -2 in the top and the bottom, and we are left with -2. So that's -2. Here, if you wanted to write an exponent, I would put that in brackets and say to the exponent 1. But really, when you have an exponent 1, it is not necessary to write, so you can just write that as -2. In the third example, we have y cubed divided by y. So the numerator is y times y times y, and the denominator is just y. Again, the exponent on the y is 1, so we just have a y in the denominator. So let's cross off a y from the top and the bottom to get y times y, which is y squared. The third example, I have -3 to the exponent 7, so I'm going to have to write that out 7 times. I'm going to put 1 in front, and then I have to divide that by -3 to the 7. So again, I have to write that out 7 times. And so now when I cross off, 1 from the top and the bottom, the second one from the top and the bottom, and keep going. And we have crossed everything out. So we are left with 1. So you may have found the rule as we were doing this. So instead of adding like we did when we were multiplying the bases, now you may have noticed that we actually subtract the exponents. So 5 take away 3 is exponent 2. 3 take away 2, we got that exponent of 1. 3 take away this exponent of 1. So 3 take away 1, we got the exponent of 2. This last example is a little tricky to see the rule because we ended up with an answer of 1. But if you take the exponents and you subtract them, you actually get the base -3 to the exponent 0. So any base to the exponent of 0 actually evaluates to 1, and it is for this reason. Everything in the numerator and the denominator cross off, leaving 1. So now let's apply the second rule that we've looked at for exponents. When we divide the same base, we subtract the exponents. So in this first example, we're going to have base 2, and we're going to take the top exponent and subtract the bottom exponent. So we get base 2 to the exponent 5. In the second example, we have base -3 to the exponent 10 divided by base -3 to the exponent of 1. So -3 to the exponent 10 take away 1, -3 to the exponent 9. Again, these brackets are necessary because the base is exponent. The brackets in example A are not necessary because the base is positive. In the next example, the base is 5, and we are going to subtract the exponent, so -4 take away -9. So be careful here, lots of negatives. We are subtracting a negative, so we are actually adding. So we're doing base 5 to -4 plus 9, so base 5 to the exponent 5. And in the last example, we have 9 squared divided by 3 squared. As the bases are not the same, we are not able to use the rules to simplify to a single power. So the second rule of exponents that we investigated says that when you divide powers with the same base, you keep that base and subtract the exponents. Now let's look at the third law of exponents, where we are given a single base with 2 exponents, and we want to write it as a single power. So here we have 2 squared, and all of that is then cubed. So we have 2 squared 3 times. So 2 squared times 2 squared times 2 squared, and then we know that 2 squared just is 2 times 2, 2 squared is 2 times 2, and 2 squared is 2 times 2. So we have 2 being multiplied by itself 6 times. So as a single power, that's 2 to the exponent 6. In the next example, we have 3 squared squared. So now I have 3 squared 2 times. So if I expand that further, that's 3 times 3 times 3 times 3. So as a single power, that's 3 to the exponent 4. The next example, I have 10 cubed. So I have 10 cubed multiplied 3 times. And that, I'm going to have to write small, is 10 times 10 times 10, which is the first bracket. And then the second bracket is again 10 times 10 times 10. And then the third one, 10 cubed, is 10 times 10 times 10. So the base is 10, and then I multiplied that by itself 9 times. So to the exponent 9. In the next example, I have base -2. It's being squared, and I'm multiplying that 4 times because the outside exponent is 4. So I have this 4 different times, and then each one means -2 times -2. This is really large, and I'm not going to be able to fit it into this box, but basically I would have -2 times -2 4 different times. So that would be base -2 to the exponent 8. And then the last example, I have base -3 cubed, and then that is being squared. So -3 cubed again, and then -3 cubed means -3 times -3 times -3, and then again I have -3 cubed, so that's -3 times -3 times -3. So the base is -3, and the exponent is 6 because I multiplied this 6 times. So take a look, see if you can make the connection between the two exponents and the exponent written as a single power, and you should see that we multiply the two exponents. So 2 times 3 gives us 6. 2 times 2 is 4. 3 times 3 is 9. 2 times 4 is 8. 3 times 2 is 6. So now let's apply that rule to these examples here. So in the first example, I have base 2, and it is being cubed, and then to the exponent 5. So I'm going to multiply the two exponents to get base 2 to the exponent 15. In the next example, I have base -3, so I definitely need brackets here. And then I have two exponents. One is negative, one is positive. So -4 times +6. So base -3. -4 times +6 is -24. In the next example, I have base -1. I'm going to multiply the two exponents, which is 3 times 5, to get 15. And I'm actually going to evaluate this one because it's very easy to do. It's just -1. Again, the base of 1 to any exponent is 1. Here the base is -1 because the exponent is odd. When I evaluate it, I get -1. In this final example, again, my base is -1 to the exponent -4, and then that is to the exponent -9, and then all of that is being multiplied by -1. So you may even want to think of this as another set of brackets in here. So I'm going to apply the -4 times -9 to this base of -1 by multiplying them. So I get -1 to -4 times -9, and then this negative in front just stays in front as well. So then I get base of -1 to the exponent +36 with that negative in front. And then I can go and evaluate this because this time the exponent is even. So the base -1 to the exponent 36 is actually evaluates to +1. And then we are multiplying that by the negative in front. So my answer is just -1 in the end. Again, be very careful not to multiply these two negatives together because you are not following the order of operations. If you do, you must evaluate the exponents first. So the final rule we have looked at says when raising a power to an exponent, you keep the same base and you multiply the exponents.